In the quiet workshops of 1935 Germany, a young physicist named Hans von Ohain stood before a principle that would change the world forever. The air around him held secrets that had waited millions of years to be unlocked: the extraordinary power of controlled explosion, the fury of burning gases harnessed not for destruction, but for the ancient dream of flight itself. Before we continue this journey, tell us where you're tuning in from, and if this story resonates with you, make sure you're subscribed, because tomorrow I've saved something extraordinary for you. Consider, for a moment, what flight meant to humanity in that era. For 32 years since the Wright brothers first lifted from the sands of Kitty Hawk, every aircraft had depended on the same fundamental principle: a spinning propeller pulling or pushing through the air. Engineers believed they had reached the absolute ceiling of possibility. The fastest fighters could barely exceed 400 miles per hour, and even those speeds came at tremendous cost in fuel and mechanical complexity. But von Ohain saw something different. Where others saw limitation, he glimpsed revolution. In his mind's eye, he could visualize Newton's third law of motion expressing itself in an entirely new way, not through the patient rotation of propeller blades, but through the violent expulsion of superheated gases. For every action, an equal and opposite reaction. The principle was elegant in its simplicity, breathtaking in its implications. The young scientist understood that flight had always been about energy transformation. Birds convert muscle power into lift, and thrust through the miracle of wing design perfected over millions of years of evolution. Propeller aircraft transform the rotational energy of engines into forward motion through carefully sculpted blades that bite into the air like underwater screws. But von Ohain envisioned something far more direct: the raw power of combustion itself, providing both the energy and the working fluid for propulsion. Working in secrecy within Ernst Heinkel's aircraft manufacturing facilities, von Ohain began constructing his first experimental engine. The concept violated everything the aviation establishment held sacred. Where conventional engines required elaborate systems of pistons, connecting rods, and crankshafts to convert the linear motion of combustion into rotational motion, von Ohain's design eliminated these mechanical complexities entirely. Air would enter the front of his engine, mix with fuel in a combustion chamber, ignite in continuous burning rather than discrete explosions, and exhaust through a precisely shaped nozzle that would accelerate the hot gases to tremendous velocity. The physics were beautiful in their directness. As burning fuel heated the air to over 1,000 degrees Celsius, the expanding gases would rush toward the only available exit, the rear of the engine. The momentum of this escaping mass would push the aircraft forward through space with a force proportional to both the mass of the exhaust and its velocity. Unlike propellers, which became less efficient as aircraft speeds increased and approached the velocity of their blade tips, this new form of propulsion would actually become more effective at higher speeds. But theory and practice occupy different worlds, and von Ohain discovered that containing and directing such violent forces presented challenges that pushed the boundaries of available materials and manufacturing techniques. The combustion chamber had to withstand temperatures that would melt ordinary steel, while the turbine blades that extracted energy from the hot gases required precision engineering beyond anything attempted in aviation. Each component demanded new metallurgical solutions, revolutionary cooling systems, and manufacturing tolerances measured in fractions of millimeters. Ernst Heinkel, the visionary aircraft manufacturer who sponsored this revolutionary work, understood that von Ohain's experiments represented far more than academic curiosity. Heinkel had built his reputation on pushing the boundaries of flight. His company's aircraft had set speed records and pioneered new aerodynamic concepts that other manufacturers struggled to match. But even Heinkel grasped that success with jet propulsion would transform not just his company's fortunes, but the entire nature of aviation itself. The experimental engine that emerged from their collaboration was designated the HES-1, a compact device that weighed only 165 pounds, yet promised to produce as much thrust as aircraft engines weighing 10 times as much. When von Ohain successfully demonstrated this first prototype in September 1937, the demonstration lasted only a few moments. But those moments proved that the concept was sound. The engine ran, the turbine blades survived the extreme temperatures, and thrust measurements confirmed the theoretical predictions. Success with the He S-1 led immediately to plans for an aircraft that could test jet propulsion in actual flight. This machine, designated the Heinkel He-178, would be humanity's first attempt to leave the Earth powered solely by the exhaust of burning gases. The aircraft that took shape in Heinkel's workshops was unlike anything previously conceived. A sleek, compact machine with its air intake positioned in the nose where conventional aircraft mounted propellers and its jet exhaust emerging from the tail. The He-178 embodied the marriage of two revolutionary concepts: von Ohein's jet engine and advanced aerodynamic principles that Heinkel's designers had been developing in parallel. The aircraft's wings swept backward slightly, presaging discoveries about high-speed flight that would not be fully understood for another decade. Its fuselage was crafted from metal rather than the fabric-covered frameworks, still common in the 1930s, and every surface was sculpted to minimize air resistance at speeds no aircraft had ever attempted. By the summer of 1939, as political tensions across Europe moved inexorably toward open warfare, the He-178 stood ready for its moment in history. The aircraft was fitted with von Ohein's third-generation engine, the He S-3, which burned diesel fuel and produced 990 pounds of thrust, enough to propel the experimental machine well beyond the speed of any conventional aircraft. On August 27, 1939, test pilot Erich Warsitz approached the waiting aircraft with the knowledge that he was about to attempt something no human being had ever done. Warsitz was no stranger to experimental flight earlier that summer. He had become the first person to fly an aircraft powered by liquid-fueled rockets, piloting Heinkel's He-176 through a series of flights that explored another revolutionary form of propulsion. But rocket flight lasted only minutes before the fuel was exhausted. This new machine promised sustained flight powered by ordinary fuel, opening possibilities that stretched beyond the horizon of imagination. The takeoff on that August morning was unlike anything Warsitz had experienced. Where rocket propulsion provided violent acceleration followed by silence, the jet engine delivered steady, continuous thrust that pushed the aircraft forward with ever-increasing velocity. As the He-178 lifted from the runway, Warsitz felt the aircraft accelerate smoothly through speeds that would have torn conventional aircraft apart. The sensation was intoxicating, a steady push that pressed him back into his seat as the aircraft climbed toward 372 miles per hour. For 6 extraordinary minutes, Warsitz piloted humanity's first jet-powered aircraft through the skies above Germany. Below him, a world still dependent on propellers and pistons went about its daily business, unaware that the age of jet flight had begun above their heads. The engine performed flawlessly, the aircraft handled with surprising grace, and when Warsitz finally throttled back and descended for landing, he carried with him the knowledge that aviation had just crossed a threshold from which there could be no return. The flight lasted only 6 minutes, but those minutes contained decades of future progress compressed into a single demonstration. Warsitz had proven that aircraft could achieve remarkable speeds by riding the exhaust of burning gases, that jet propulsion could be both practical and reliable, and that the theoretical limit of propeller-driven flight was not the limit of human flight itself. Word of the successful flight reached the highest levels of German government within hours, but the response revealed how dramatically new technologies can challenge established thinking. Officials who witnessed later demonstrations saw an interesting experiment, but failed to grasp that they were observing the birth of a new age. The aircraft seemed too small, too experimental, too removed from the massive bombers and fighters that dominated their strategic thinking. Ernst Udet and Erhard Milch, leaders of the German aviation establishment, watched the He-178 perform and pronounced themselves unimpressed. They saw an aircraft that could barely carry weapons, that required exotic fuels, that depended on manufacturing techniques their factories had never attempted. They failed to envision squadrons of jet fighters sweeping conventional aircraft from the skies, or to understand that the 6-minute flight they had just witnessed would eventually shrink the world itself. But in workshops across Germany, engineers and designers who understood the implications began their own secret projects. If Heinkel could build one jet aircraft, others could build better ones. If von Ohain could create one jet engine, competing teams could develop more powerful versions. The race to perfect jet propulsion had begun, driven by minds that recognized the difference between incremental improvement and revolutionary transformation. The He-178 would fly only a few more times before being placed in a Berlin museum, where it would eventually be destroyed by Allied bombing in 1943. But the principles it demonstrated lived on in the minds of engineers who had witnessed the impossible become routine. In hidden facilities across the Reich, new projects took shape, aircraft designed from the outset to harness the tremendous power of jet propulsion, not for 6-minute demonstrations, but for the deadly serious business of aerial warfare. As 1939 drew to a close and Europe plunged into global conflict, the age of jet flight remained hidden from the world. Allied intelligence services had no idea that German engineers had unlocked the secret of PERV, high-speed flight, no conception that their own propeller-driven fighters and bombers would soon face adversaries moving at speeds they could not match. The forbidden flight of August 27th had opened a door to the future, but that future remained concealed behind the growing thunder of conventional war. Soon, very soon, the world would discover what humanity could achieve when the fury of controlled explosion carried aircraft beyond the boundaries of everything previously thought possible. Tomorrow, we'll witness how this extraordinary discovery ignited a secret competition between two brilliant aircraft designers, each determined to transform von Ohain's experimental success into the world's first combat-ready jet fighter. The race that followed would push the boundaries of engineering, human endurance, and the physics of flight itself. The success of the He-178 had revealed a profound truth about human innovation, that revolutionary discoveries create their own momentum, inspiring competing minds to push even further beyond the boundaries of possibility. By the winter of 1939, two of Germany's most brilliant aircraft designers found themselves locked in a race that would determine not just which company would dominate the future of aviation, but which vision of jet-powered flight would carry humanity into the age of supersonic war. Ernst Heinkel understood that his company's triumph with the world's first jet aircraft was only the beginning. The He-178 had proven the concept, but 6 minutes of experimental flight bore little resemblance to the sustained combat operations that modern warfare demanded. Heinkel's engineers needed to create something far more ambitious, a true fighting machine that could harness jet propulsion's tremendous potential while surviving the brutal realities of aerial combat. Working in absolute secrecy, Heinkel's design team began developing what they designated the He-180, later redesignated the He-280. This aircraft would embody everything they had learned from von Ohain's pioneering engine work, but scaled up for military service. Where the He-178 had been a proof of concept, the He-280 would be a weapon of war. The aircraft that emerged from Heinkel's workshops seemed to have arrived from a future that conventional aviation had not yet imagined. Twin turbojets mounted beneath gracefully swept wings provided twice the thrust of the experimental single engine, while the aircraft's sleek fuselage incorporated aerodynamic principles that pushed the boundaries of contemporary understanding. But perhaps most revolutionary of all was the He-280's landing gear configuration, a tricycle arrangement with the main wheels positioned behind the center of gravity and a nose wheel at the front. This tricycle gear represented far more than mechanical innovation. Conventional aircraft of the era used tailwheel configurations that placed the main landing gear ahead of the center of gravity, causing the aircraft to sit with its nose pointed slightly upward while on the ground. This arrangement worked adequately for propeller-driven aircraft, but created serious problems for jets. The upward angle of jet engines on tailwheel aircraft would direct their exhaust downward, potentially damaging runways and creating dangerous debris clouds. Tricycle gear allowed jet aircraft to sit level on the ground, pointing their engine exhaust safely backward. But Heinkel's innovations extended far beyond landing gear geometry. The He-280 incorporated the world's first operational ejection seat, a device that could blast a pilot clear of his aircraft in milliseconds using compressed air pressure equivalent to a small explosion. The seat represented an acknowledgement that jet aircraft would operate in realms of speed and violence, where conventional escape methods might prove inadequate. If something went catastrophically wrong at 400 miles per hour, a pilot would need extraordinary means of survival. The ejection seat embodied the intersection of necessity and ingenuity that characterized jet aircraft development. Engineers recognized that pushing the boundaries of flight speed inevitably increased the risks faced by test pilots and combat aviators. Rather than accepting these risks as unavoidable, they created entirely new safety systems that turned the violence of explosive charges into life-saving force. The compressed air ejection mechanism could accelerate a pilot and his seat to velocities sufficient to clear the aircraft's tail surfaces, while deploying a parachute that would bring him safely to Earth. Meanwhile, in the workshops of Messerschmitt AG, Willy Messerschmitt pursued his own vision of jet-powered combat aircraft. Messerschmitt had built his reputation on creating fighters that combined devastating firepower with exceptional performance aircraft like the Bf 109 that had established German air superiority over Europe through their lethal effectiveness in combat. Now he faced the challenge of translating that success into the realm of jet propulsion. Messerschmitt's approach differed fundamentally from Heinkel's philosophy. Where Heinkel prioritized elegance and aerodynamic sophistication, Messerschmitt focused on rugged reliability and overwhelming firepower. His Project 1065, which would evolve into the Me-262, embodied a more conservative approach to jet aircraft design that emphasized proven engineering solutions over revolutionary innovations. The Me-262's configuration reflected Messerschmitt's practical military experience. The aircraft featured a conventional fuselage design that housed the pilot, fuel, and armament in a layout similar to successful propeller-driven fighters. Its wings swept backward at an 18-degree angle, not because Messerschmitt fully understood the aerodynamic advantages of sweep, but because mounting the engines beneath straight wings would have required impossibly long landing gear to provide ground clearance. This accidental discovery of swept-wing benefits would prove prophetic. As aircraft approached the speed of sound, conventional straight wings began experiencing dangerous aerodynamic phenomena that could tear an aircraft apart. Swept wings delayed these effects by reducing the effective speed of air flowing over the wing surfaces, allowing aircraft to operate safely at velocities that would destroy straight-winged designs. Messerschmitt had stumbled upon one of the most important aerodynamic principles of the jet age, while simply trying to solve a practical ground clearance problem. The competition between Heinkel and Messerschmitt represented more than corporate rivalry. It embodied two fundamentally different approaches to revolutionary technology. Heinkel pursued the path of radical innovation, creating aircraft that incorporated multiple breakthrough concepts simultaneously. The He-280's tricycle gear, ejection seat, and advanced engine mounting represented a complete reimagining of how fighter aircraft should be designed and operated. Messerschmitt, by contrast, followed an evolutionary approach that applied jet propulsion to proven fighter design principles. The Me-262 retained familiar cockpit layouts, conventional armament arrangements, and structural concepts that had already demonstrated their effectiveness in combat. This conservative philosophy would prove advantageous when the pressures of wartime production demanded aircraft that could be manufactured quickly by workers familiar with existing techniques. The engines that would power these competing designs presented their own extraordinary challenges. Both aircraft depended on turbojet technology that remained in its experimental infancy, with metallurgical requirements that pushed beyond the capabilities of existing manufacturing processes. The turbine blades that extracted energy from burning gases had to withstand temperatures exceeding 1,000 degrees Celsius while rotating at speeds that generated centrifugal forces equivalent to thousands of times their own weight. Creating these turbine blades required new alloys that combined heat resistance with mechanical strength materials that incorporated rare metals like nickel, chromium, and cobalt in precisely controlled proportions. The manufacturing process demanded tolerances measured in fractions of millimeters, with each blade individually balanced to prevent vibrations that could destroy the entire engine. A single imperfection in metallurgy or manufacturing could cause catastrophic failure at 20,000 feet. transforming cutting-edge aircraft into falling debris in seconds. Test pilots who flew these experimental machines found themselves entering a realm of flight that human beings had never experienced. The acceleration provided by jet engines was unlike anything possible with propeller-driven aircraft, a steady, continuous push that pressed pilots back into their seats as velocities climbed toward the speed of sound itself. The sensation was both exhilarating and terrifying, as pilots discovered that their aircraft could reach speeds where conventional control responses no longer applied. At 300 miles per hour, a propeller-driven fighter responded predictably to control inputs, with changes in direction occurring smoothly and progressively. But as jet aircraft approached 450 miles per hour, they entered a realm where aerodynamic forces behaved differently. Control surfaces that provided adequate authority at lower speeds became sluggish and ineffective at high velocity, while structural loads increased exponentially with speed. Pilots reported that flying these experimental jets required completely new techniques and mental approaches. The aircraft demanded smooth, gentle control inputs rather than the aggressive maneuvering possible with slower aircraft. Sharp turns or abrupt control movements could overstress the airframe or cause dangerous loss of control, while the tremendous speeds made precise navigation and landing approaches far more challenging. Perhaps most unsettling was the realization that these aircraft operated in a speed regime where human reaction times became inadequate for emergency situations. Events that unfolded over several seconds in propeller-driven aircraft now occurred in fractions of a second. Engine failures, structural problems, or combat damage required immediate responses that tested the limits of human reflexes and decision-making capabilities. By 1941, both competing designs had advanced to the point where powered flight tests could begin. The He-280 first flew on March 30, 1941, with test pilot Fritz Schaefer reporting that the aircraft handled reasonably well despite some difficulty in turns. The sensation of flying without propeller noise or vibration was described as eerily smooth, with only the sound of air flowing over the aircraft's surfaces and the distant whistle of the turbojet engines. The Me-262 followed with its first jet-powered flight on July 18, 1942, when test pilot Fritz Wendell discovered that Messerschmitt's creation could reach velocities that left contemporary aircraft far behind. The swept-wing configuration that had been adopted for practical reasons proved to provide exceptional stability at high speeds, while the aircraft's heavier construction absorbed the stresses of jet-powered flight without structural failure. As both aircraft accumulated test flights and performance data, German aviation authorities began to recognize that they possessed technology that could revolutionize aerial warfare. Intelligence reports indicated that Allied aircraft development remained focused on improving propeller-driven designs, with no apparent awareness that jet propulsion had progressed beyond experimental curiosity to practical military application. The strategic implications were staggering. Fighter aircraft that could fly 100 miles per hour faster than anything the Allies possessed would not just achieve air superiority, they would make Allied air operations virtually impossible. Bomber formations that depended on fighter escorts for protection would find themselves defenseless against interceptors that could approach from any direction at speeds that made evasion impossible. But translating experimental success into operational capability required solving problems that extended far beyond aerodynamics and propulsion. Manufacturing jet engines demanded new industrial processes, specialized tooling, and workforce training that conventional aircraft production had never required. The rare metals essential for turbine blade construction had to be imported from distant countries or extracted from limited domestic sources, creating supply vulnerabilities that could cripple production. Most critically, the transition from experimental prototypes to combat-ready aircraft required resolving the fundamental tension between innovation and reliability. Test pilots could accept engine failures and mechanical problems as part of exploring new technology, but combat pilots needed aircraft that would function predictably under the stress of aerial warfare. Every component had to be refined, tested, and proven capable of surviving not just normal operations, but the extreme conditions of combat damage, harsh weather, and intensive maintenance schedules. As 1942 drew to a close, both the He-280 and Me-262 had demonstrated that jet-powered fighter aircraft were not only possible, but inevitable. The question that remained was which design would reach operational status first, and whether German industry could produce these revolutionary machines in sufficient numbers to affect the course of the war itself. The race toward tomorrow had become a race against time, with the future of aerial warfare hanging in the balance. Soon, very soon, the theoretical advantages of jet propulsion would face their ultimate test in the deadly skies above Europe, where innovation would meet destruction in battles that would determine which vision of flight would carry humanity into the supersonic age. April 19, 1944, dawned clear over the Reich's embattled airspace, but this morning would witness something that transformed science fiction into deadly reality. After years of secret development and testing, the Messerschmitt Me-262 Schwalbe was about to enter combat over Europe, and with it, humanity would cross the threshold into an age of warfare that moved faster than human reflexes could follow. The aircraft that emerged from hidden German factories bore little resemblance to the propeller-driven fighters that had dominated aerial combat since the Wright brothers first lifted from the Earth. The Me-262's swept wings cut through the air with mathematical precision, while its twin Junkers Jumo 004 turbojet engines promised performance that would render every Allied aircraft obsolete overnight. At 540 miles per hour, this sleek Predator could outrun anything the Allies had built, and its revolutionary design represented a quantum leap beyond conventional aviation that no amount of incremental improvement could match. The pilot who first demonstrated the Me-262's combat potential was Lieutenant Alfred Schreiber, a veteran aviator who had spent years mastering the art of aerial warfare in propeller-driven machines. But nothing in Schreiber's extensive experience had prepared him for the extraordinary sensation of acceleration that jet propulsion provided. Where conventional fighters required careful management of engine power and propeller pitch, the jets delivered steady, continuous thrust that pressed pilots deep into their seats as velocities climbed toward previously unimaginable speeds. On July 26, 1944, Schreiber found himself pursuing a British de Havilland Mosquito reconnaissance aircraft through the skies above Munich. The Mosquito represented one of the fastest operational aircraft in Allied service, a twin-engine design capable of exceeding 400 miles per hour that routinely outran German interceptors through sheer speed. Its pilot, Flight Lieutenant R.E. Wall, had grown accustomed to the comfortable knowledge that few German aircraft could match his machine's velocity, and none could sustain pursuit for more than a few minutes. But as Schreiber's Me-262 closed the distance with mathematical inevitability, Wall realized that he faced something entirely outside his experience. The German aircraft approached from behind with a speed differential that made evasion virtually impossible, while its sleek profile and unusual engine configuration marked it as technology that Allied intelligence had never encountered. For the first time in the war, a German fighter was not just matching Allied performance, it was exceeding it by margins that transformed the fundamental mathematics of aerial combat. The engagement that followed became the first documented encounter between jet and conventional aircraft, a moment when the future collided with the past at 500 miles per hour. Schreiber positioned his aircraft for attack with the confidence that came from overwhelming speed advantage, knowing that his target could neither outrun nor outmaneuver the revolutionary machine beneath his hands. The Me-262's 430mm Mk108 cannons represented firepower that could destroy a heavy bomber with a single well-placed burst, while its swept wings remained stable and controllable at velocities that would tear conventional aircraft apart. Wall, recognizing the impossible situation he faced, threw his Mosquito into evasive maneuvers that pushed both aircraft and pilot to their absolute limits. The chase that ensued demonstrated the dramatic transformation that jet propulsion had brought to aerial warfare, where dogfights between propeller-driven aircraft involved intricate dance-like maneuvers that could continue for minutes. This engagement compressed those same deadly interactions into seconds of violence that unfolded faster than human thought could follow. Through 3 attack runs, Schreiber pressed his advantage while Wall fought for survival with skills honed through years of combat experience. The Mosquito pilot discovered that conventional evasive tactics, sharp turns, altitude changes, and speed variations that worked against propeller-driven pursuers proved inadequate against an aircraft that could match every maneuver while maintaining superior velocity. The jet's swept wings provided stability at high speeds that allowed precise gunnery even during aggressive maneuvering, while its tremendous power reserves meant that altitude changes and acceleration bursts that would exhaust conventional engines barely affected its performance. Yet Wall's desperate maneuvering ultimately saved his life. The Me-262's overwhelming speed advantage proved to be a double-edged sword in close combat, as Schreiber found himself repeatedly overshooting his target and requiring time to reposition for subsequent attacks. The jet's tremendous velocity made precise gunnery challenging when pursuing an evasively maneuvering target, while its swept wings, optimized for high-speed flight, provided less maneuverability than conventional designs at lower velocities. The engagement ended when Wall managed to escape across the border into Allied-controlled territory, carrying with him intelligence that would transform Allied understanding of German technological capabilities. His Mosquito had sustained damage during the encounter, reportedly losing a hatch during the violent, evasive maneuvering. But both aircraft and pilot survived to deliver the alarming news that Germany had achieved a breakthrough in aviation, technology that rendered Allied air superiority suddenly vulnerable. The psychological impact of this first jet encounter extended far beyond the immediate tactical situation. Allied airmen who had grown confident in their technological superiority suddenly faced the realization that German engineers had leaped decades ahead in aviation development. Intelligence analysts studying Wall's report struggled to comprehend how German industry, supposedly crippled by Allied bombing and resource shortages, had managed to develop and deploy aircraft that moved faster than anything in Allied service. As word of the jet encounter spread through Allied air commands, the implications became increasingly clear. Fighter, escorts that protected bomber formations by matching or exceeding enemy interceptor speeds, would find themselves helpless against aircraft that could approach from any direction, at velocities that made interception virtually impossible. Bomber crews who had learned to depend on fighter protection and defensive gunnery for survival would face attackers that could strike without warning and disappear before defensive measures could respond. The Me-262's combat debut marked more than tactical innovation. It represented the emergence of warfare that moved faster than human senses could process. Conventional aerial combat had unfolded at speeds that allowed pilots to see, evaluate, and respond to developing situations. But jet combat compressed those same interactions into timeframes that challenged the limits of human reaction capabilities, creating new forms of violence that demanded completely different tactical approaches. German pilots who transitioned from propeller-driven fighters to jets discovered that their aircraft's tremendous speed advantage came with corresponding challenges that conventional training had never addressed. The closing speeds possible when jet aircraft engaged each other reached velocities where target identification, gunnery solutions, and evasive maneuvering had to be completed in fractions of seconds. Pilots found themselves fighting battles that moved faster than conscious thought, where split-second decisions determined survival or destruction. The firepower that jet fighters brought to aerial combat was as revolutionary as their speed. The Me-262's 430mm cannons could deliver more destructive force in a single burst than entire squadrons of conventional fighters. These weapons fired explosive shells that could tear apart heavy bombers or destroy enemy fighters with a single hit, while their high muzzle velocity provided flat trajectories that simplified gunnery at the extreme ranges possible with jet aircraft speeds. Allied bomber crews began reporting encounters with German fighters that moved like lightning bolts across the sky, appearing from empty air and vanishing before gunners could track their targets. The psychological effect of facing aircraft that could strike without warning and escape beyond retaliation fundamentally altered the mental experience of aerial warfare. Bomber formations that had learned to fight their way through determined but predictable opposition suddenly faced attackers that seemed to operate by entirely different physical laws. The swept wings that gave jet fighters their high-speed stability also provided aerodynamic characteristics that conventional aircraft could not match. where straight wings lost effectiveness as aircraft approached the speed of sound. Swept configurations delayed the onset of compressibility effects that could cause catastrophic control loss. This allowed jet fighters to operate safely in speed regimes where conventional aircraft would experience violent buffeting, control reversal, or structural failure. But perhaps most significantly, the emergence of jet fighters marked humanity's first operational encounter with the physics of transonic flight, the dangerous realm between subsonic and supersonic speeds, where aerodynamic forces behave unpredictably. Test pilots, pushing Me-262s to their performance limits, discovered that their aircraft could approach the speed of sound itself, entering a twilight zone of flight where conventional aerodynamic theory broke down and new phenomena emerged. As the summer of 1944 progressed, encounters between jets and conventional aircraft became increasingly common over European skies. Each engagement demonstrated the hopeless mismatch between aircraft separated by generational leaps in technology. Allied fighter pilots who had dominated aerial combat through superior training and tactical innovation found themselves facing opponents whose machines provided advantages that no amount of skill could overcome. The strategic implications rippled through every level of Allied air operations. Bombing missions that had been planned based on known German fighter capabilities suddenly faced interceptors that could appear without warning, strike with devastating effectiveness, and escape before escort fighters could respond. The careful calculations of fighter escort ranges, bombing altitudes, and mission timing that had been developed through years of combat experience became obsolete overnight. Intelligence services raced to understand how Germany had achieved such a dramatic technological breakthrough while simultaneously fighting a multi-front war that supposedly exhausted their industrial capacity. The jets represented not just individual aircraft, but entire new systems of manufacturing, materials, science, and engineering capability that Allied analysts had failed to detect despite extensive reconnaissance and espionage efforts. As reports of jet encounters accumulated, Allied air commanders faced the disturbing realization that their overwhelming numerical superiority might prove meaningless against aircraft that could engage and disengage at will. The mathematical advantage of fielding thousands of conventional fighters against hundreds of jets became questionable when those jets could choose the terms of every engagement while remaining virtually immune to retaliation. The age of jet warfare had arrived with the violence of contained explosion, transforming the skies above Europe into a realm where the future battled the past at speeds that challenged the very limits of human perception. Tomorrow, we will discover how Allied pilots learned to exploit the hidden vulnerabilities that even these revolutionary machines could not escape, and how the promise of invincibility that jet fighters seemed to offer would prove as fragile as the rare metals that powered their revolutionary engines. The extraordinary speed that made jet fighters seemingly invincible contained within its very nature the seeds of vulnerability that would ultimately limit their effectiveness. Like all revolutionary technologies, the Me-262's greatest strength proved inseparable from weaknesses that careful observation and tactical innovation could exploit. Allied pilots, faced with an enemy that outran everything in their arsenal, began studying the new German fighters with the desperate intensity of prey that must understand its predator to survive. The first crucial insight emerged from watching jet fighters during their most vulnerable moments, the critical phases of takeoff and landing, when even the most advanced aircraft became temporarily helpless. Unlike propeller-driven fighters that could operate effectively on a single engine, jets required both power plants functioning properly to maintain adequate thrust for safe flight. During the delicate ballet of landing approaches, when pilots reduced power to descend toward runway thresholds, jets operating on one engine faced performance limitations that made them easy targets for conventional fighters lurking near German airfields. Captain Chuck Yeager, the American test pilot who would later become the first human to exceed the speed of sound, discovered this vulnerability during a combat mission over Germany. Yeager observed a damaged Me-262 attempting to return to its base with one engine shut down, and recognized that the jet's legendary speed advantage had evaporated entirely. The crippled aircraft could barely maintain altitude, while its single functioning engine provided insufficient power for evasive maneuvering or acceleration. The physics of single-engine jet operation created a death trap that no amount of pilot skill could overcome. With only half its designed thrust available, and Me-262 could not climb rapidly, accelerate quickly, or maintain speed during turns. These limitations transformed the world's most advanced fighter into a sluggish target that conventional aircraft could pursue and destroy with relative ease. Allied pilots learned to patrol German airfields, waiting patiently for jets to approach in their most vulnerable configuration. This tactical discovery led to the development of systematic airfield attacks that focused not on destroying jets in the air, but on catching them during takeoff and landing phases when their advantages disappeared. Allied fighter pilots began timing their attacks to coincide with known jet patrol schedules, positioning themselves to intercept returning aircraft when fuel states and engine stress made extended combat impossible. But the jet's vulnerabilities extended far beyond operational limitations to encompass fundamental engineering challenges that German industry struggled to overcome. The Junkers Jumo 004 engines that powered the Me-262 represented technological achievements that pushed beyond the boundaries of available material science, creating power plants that delivered extraordinary performance at the cost of shocking unreliability. These revolutionary engines averaged only 12.5 hours of operation before requiring complete replacement, a service life so brief that jet squadrons consumed engines faster than German factories could produce them. The turbine blades that extracted energy from burning gases operated under conditions so extreme that metallurgical failures occurred with frightening regularity. Temperatures exceeding 1,000 degrees Celsius, combined with rotational speeds that generated centrifugal forces, equivalent to thousands of times the blade's own weight, created stresses that exceeded the capabilities of available alloys. German engineers had discovered that jet engine construction required exotic metals, nickel, chromium, cobalt, and other rare elements that provided the heat resistance and mechanical strength essential for turbine blade survival. But Germany's wartime economy, increasingly isolated by Allied blockades and territorial losses, could no longer obtain adequate supplies of these critical materials. Engineers found themselves forced to redesign turbine components using substitute alloys that possessed inferior properties, creating engines that failed unpredictably and catastrophically. The metallurgical challenges extended beyond simple material availability to encompass manufacturing processes that demanded precision beyond conventional aircraft engine production. Each turbine blade required individual balancing to prevent vibrations that could destroy entire engines, while tolerances measured in fractions of millimeters determined the difference between reliable operation and catastrophic failure. German factories, operating under constant Allied bombing attacks and staffed by increasingly inexperienced workers, struggled to maintain the quality standards that jet engines demanded. Fuel shortages created additional operational restrictions that limited jet effectiveness, even when engines functioned properly. The special synthetic fuels that turbojet engines required consumed resources that Germany's economy could ill afford, while transportation difficulties often prevented adequate fuel supplies from reaching operational airfields. Jet squadrons frequently remained grounded for weeks at a time, their revolutionary aircraft rendered useless by empty fuel tanks rather than enemy action. Allied intelligence services gradually pieced together the scope of German logistical challenges through careful analysis of captured equipment and interrogation of prisoners. They discovered that despite producing over 1,400 Me-262s, German forces could rarely maintain more than 25 operational aircraft at any given time. The remainder sat in hangars awaiting engine replacements, fuel deliveries, or spare parts that German industry could no longer provide in adequate quantities. Maintenance requirements further limited jet availability by demanding specialized knowledge and equipment that conventional aircraft servicing had never required. Jet engines could not be repaired by mechanics trained on piston power plants, while the specialized tools needed for turbine assembly and balancing remained scarce throughout the German maintenance system. Simple repairs that conventional fighters could receive at forward airfields required jets to return to factory facilities, where expert technicians possessed the skills and equipment necessary for turbojet servicing. The underground factories where German industry attempted to protect jet production from Allied bombing represented marvels of engineering and desperation in equal measure. Skilled craftsmen worked by artificial light in tunnels carved from solid rock, assembling precision turbine components while Allied bombs fell on the landscape above their heads. These subterranean workshops produced engines that met the demanding specifications jet aircraft required. But their limited capacity and difficult working conditions prevented the mass production that military effectiveness demanded. Allied bombing campaigns specifically targeted the transportation networks that supplied these hidden factories with raw materials and specialized components. Railroad lines, highways, and waterways that carried rare metals and precision parts from suppliers to manufacturers faced constant interdiction that disrupted production schedules and created cascading shortages throughout the German aviation industry. Even when underground factories remained undamaged, their output declined as supply chains collapsed under sustained attack. The human cost of pushing jet technology beyond the limits of available materials and manufacturing capability manifested in engine failures that occurred without warning during critical flight phases. German pilots learned to treat their engines with extreme caution, avoiding rapid throttle movements or sustained high-power operation that could trigger catastrophic turbine failures. This conservative approach to engine management reduced the jet's tactical effectiveness by preventing pilots from fully exploiting their aircraft's performance advantages. Engine fires represented a particularly terrifying failure mode that could consume an entire aircraft in seconds. When turbine blades failed at high rotational speeds, the resulting fragments could puncture fuel lines, ignite hydraulic systems, or damage control surfaces with consequences that unfolded faster than human reaction times. Pilots who experienced engine fires faced impossible choices between attempting emergency landings with aircraft that might explode at any moment or ejecting over enemy territory where capture awaited. The ejection seats that Heinkel had pioneered as safety equipment for high-speed aircraft proved essential for jet pilot survival. But their compressed air operation added another layer of mechanical complexity that required constant maintenance. Ejection seat failures during emergencies cost lives that conventional safety equipment might have saved, while the psychological stress of flying aircraft that required explosive escape systems affected pilot performance and morale. Weather conditions that posed manageable challenges for conventional aircraft became serious threats for jets operating at the margins of their performance envelopes. Rain ingestion could cause engine flameouts that left pilots flying unpowered gliders, while ice formation on air intakes reduced thrust to levels that made sustained flight impossible. German jet pilots learned to avoid adverse weather conditions that their propeller-driven counterparts navigated routinely, further limiting operational flexibility. The tactical implications of these cumulative vulnerabilities gradually shifted the balance of aerial warfare back toward Allied forces, despite the jet's theoretical advantages. German jet squadrons found themselves constrained by fuel availability, engine reliability, and weather conditions that rarely affected conventional aircraft operations. Mission planning became an exercise in managing multiple limiting factors that could ground entire units, regardless of strategic requirements or tactical opportunities. Allied pilots developed increasingly sophisticated tactics for exploiting jet vulnerabilities, once they understood the operational constraints that limited German effectiveness. Fighter sweeps timed to coincide with known fuel exhaustion periods caught jets returning to base with insufficient power reserves for extended combat. Attacks on airfield approach routes targeted jets during their most vulnerable flight phases, when single-engine operation made evasion impossible. The promise of invincibility that jet technology had seemed to offer proved as fragile as the exotic metals that powered these revolutionary machines. Superior performance could not overcome the industrial limitations, material shortages, and manufacturing challenges that constrained German jet operations throughout the final year of the war. Tomorrow, we will explore how political interference and strategic miscalculations magnified these technical challenges, transforming what might have been Germany's salvation into a testament to the dangers of developing revolutionary technology under the pressures of desperate circumstances. November 26, 1943, witnessed one of the most consequential demonstrations in aviation history, yet its outcome would prove how political interference can transform technological triumph into strategic disaster. At the German military airfield at Insterburg in East Prussia, Adolf Hitler stood before an array of revolutionary weapons that represented Germany's most advanced technological achievements. But the decision he would make that day revealed how leadership divorced from technical reality can destroy even the most promising innovations. The centerpiece of this carefully orchestrated display was the Messerschmitt Me 262, its swept wings and sleek fuselage gleaming in the East Prussian sunlight. Beside it sat an Arado R-234 twin-jet reconnaissance bomber, hastily transported and reassembled for this critical demonstration. These aircraft embodied years of secret development and engineering breakthrough that had given Germany an unprecedented advantage in aviation technology. Yet Hitler's reaction to what he witnessed would nearly destroy the program that created them. Willy Messerschmitt himself served as guide for this demonstration, understanding that his company's future depended on convincing the Führer that jet fighters represented Germany's best hope for regaining air superiority over Europe. The aircraft before them could outfly anything the Allies possessed, while their revolutionary design principles pointed toward a future of aerial warfare that conventional aviation could never match. Yet Messerschmitt could not anticipate how completely Hitler would misunderstand what he was observing. Reich Minister of Armaments Albert Speer, Reichsmarschall Hermann Göring, and Luftwaffe Inspector General Erhard Milch accompanied Hitler through the display, each hoping that the demonstration would finally convince Germany's leadership to fully support jet aircraft development. They had witnessed the test flights that proved these machines could achieve speeds that rendered Allied fighters obsolete, while their firepower promised to devastate bomber formations that had been laying waste to German cities with increasing impunity. But Hitler's mind focused not on air-to-air combat capabilities, but on his desperate desire for weapons that could strike back at Allied population centers. The Führer had become obsessed with retaliation following the Allied bombing campaigns that were felony, reducing German cities to rubble, and he viewed every new weapon through the lens of its potential for revenge rather than its optimal military application. When he looked at the Me 262, he saw not an interceptor designed to destroy enemy bombers, but a fast bomber that could carry German vengeance to Allied cities. The moment that would seal the program's fate came when Hitler asked a seemingly innocent question. Can this aircraft carry bombs? Messerschmitt, eager to demonstrate his design's versatility, confirmed that the Me 262 could indeed be modified to carry external bomb loads, though this would compromise the speed and agility that made it effective as a fighter. Hitler seized upon this capability with an enthusiasm that horrified the aviation experts present, immediately demanding that the revolutionary fighter be developed primarily as a bomber rather than an interceptor. This decision represented a fundamental misunderstanding of how air warfare had evolved by 1943. Germany's most pressing need was for interceptors that could break up Allied bomber formations before they reached their targets, exactly the mission for which the Me 262 had been designed. Converting these aircraft into bombers would sacrifice their natural advantages while attempting to duplicate capabilities that conventional aircraft could provide more effectively. Yet Hitler's obsession with retaliation overrode all military logic. The technical implications of Hitler's demand proved devastating for the Me 262's development timeline and operational effectiveness. Engineers who had optimized the aircraft for air-to-air combat found themselves forced to redesign critical systems for ground attack missions that required completely different capabilities. The swept wings that provided exceptional high-speed stability became less advantageous for low-altitude bombing runs, while the heavy cannon armament that could destroy enemy fighters proved less useful than conventional bombs for attacking ground targets. Modifying the Me 262 for bombing missions required structural changes that delayed production by crucial months, while German cities continued burning under Allied attack. The external bomb racks needed to carry explosive payloads, added weight and drag that reduced the aircraft's speed advantage, while the fire control systems optimized for air-to-air gunnery required replacement with bombing equipment that German industry had never produced for jet aircraft. Perhaps most critically, Hitler's bomber obsession diverted approximately 30% of Me 262 production, from fighter variants to attack aircraft that could never justify their enormous development and manufacturing costs. Each jet converted to bombing configuration represented one less interceptor available to defend German airspace, while the modified aircraft proved less effective in their new role than conventional bombers that could carry larger payloads over greater distances. The political infighting that Hitler's decision triggered created additional delays and confusion that further undermined the program's effectiveness. Hermann Göring, whose Luftwaffe desperately needed interceptors to combat Allied bombing, found himself fighting against Hitler's direct orders while simultaneously competing with Albert Speer for control over jet aircraft production priorities. This bureaucratic warfare consumed time and resources that German industry could ill afford, while Allied bombers continued their systematic destruction of German manufacturing capacity. Willy Messerschmitt discovered that success in Nazi Germany's political environment required skills entirely different from engineering excellence or aviation expertise. Navigating the competing demands of Hitler, Göring, and Speer, while maintaining production schedules and technical standards, proved nearly impossible when political objectives contradicted military necessity. Engineers who should have focused on solving technical challenges instead spent months redesigning aircraft to satisfy political requirements that undermined their operational effectiveness. The psychological impact on German pilots proved equally damaging as the technical delays and political interference. Experienced aviators who had eagerly anticipated flying the world's most advanced fighters found themselves assigned to bombing missions that negated their aircraft's revolutionary capabilities. The transition from air-to-air combat to ground attack required completely different training and tactical approaches, while the modified aircraft handled differently from the fighters pilots had learned to fly. Pilot training programs that had been developed specifically for jet fighter operations required extensive revision to accommodate Hitler's bombing requirements. The delicate techniques needed to manage temperamental jet engines during high-speed interceptor missions proved less relevant for low-altitude attack profiles that emphasized precision bombing over aerial combat. This training disruption occurred at the worst possible moment, when Germany's most experienced pilots needed to master jet aircraft before Allied air superiority became absolute. The fuel and maintenance requirements that already constrained jet operations became even more restrictive when aircraft designed for short-duration interceptor missions were assigned to longer-range bombing sorties. The Junkers Jumo 004 engines that provided adequate endurance for defensive operations proved marginal for attack missions that required sustained flight over enemy territory. Engine failures that forced emergency landings in friendly territory during interceptor operations became capture situations when bombers went down behind enemy lines. Quality control suffered as German factories struggled to produce both fighter and bomber variants simultaneously, while operating under constant Allied bombing attacks. The precision manufacturing that jet engines required became increasingly difficult to maintain when production lines had to accommodate multiple configurations with different requirements and specifications. Workers who had finally mastered the complex procedures needed for jet fighter assembly found themselves retraining for bomber production that demanded different skills and quality standards. The strategic opportunity that Germany might have exploited through focused jet fighter development slipped away during the months consumed by political interference and mission redefinition. Allied bomber formations that had been vulnerable to concentrated jet interceptor attacks adapted their tactics and defensive measures, while German engineers struggled with bombing modifications that diverted resources from fighter production. The window of maximum effectiveness gradually closed, as delays allowed Allied countermeasures to evolve. By January 1945, when Hitler finally authorized formation of pure fighter units like Jagdgeschwader 7 and Lieutenant General Adolf Galland's elite Jagdverband 44, Allied air superiority over Germany had become so complete that even perfect jet fighters could not have reversed the strategic situation. The concentrated application of jet technology that might have disrupted Allied bombing campaigns in 1943 arrived too late to affect the war's outcome, though individual encounters continued to demonstrate the devastating potential that political interference had squandered. Gallen's squadron of veteran aces flying unmodified. Me-262 fighters achieved remarkable success during their brief operational period, proving what concentrated jet fighter operations might have accomplished if implemented earlier. On March 18, 1945, 37 jets intercepted a formation of 1,221 Allied bombers escorted by 632 fighters, shooting down 12 bombers and 1 fighter, while losing only 3 jets. This engagement demonstrated the tactical effectiveness that systematic political interference had prevented from achieving strategic significance. The lesson embedded in the Me-262's tragic transformation from revolutionary fighter to compromised bomber reveals how political leadership disconnected from technical reality can destroy even the most promising innovations. Hitler's decision to prioritize revenge over military effectiveness transformed Germany's greatest aviation achievement into a cautionary tale about the dangers of political interference in technological development. Tomorrow, we will explore how this squandered opportunity ultimately benefited Germany's enemies, as Allied forces captured the knowledge and expertise that political mismanagement had prevented from achieving its full potential. May 8, 1945, marked not only Germany's surrender and the end of European warfare, but the beginning of the most extraordinary technology transfer in aviation history. As Allied forces swept across the collapsing Reich, they discovered the full scope of German jet development, a treasure trove of revolutionary knowledge that would accelerate aviation progress by decades and lay the foundation for the jet age that would transform human civilization itself. The race to capture German jet technology began even before the formal surrender, as American, British, and Soviet intelligence teams competed to secure the most valuable prizes of technological warfare. Operation Paperclip, the American program to recruit German scientists and engineers, had been planning since 1944 to prevent advanced German research from falling into Soviet hands, but nothing had prepared Allied investigators for the breadth and sophistication of the jet aircraft program they would uncover in hidden factories and secret research facilities across Germany. At Oberammergau, American forces discovered manufacturing facilities where Messerschmitt had continued producing Me-262s in underground workshops carved from solid rock. These subterranean factories contained not only completed aircraft but also the specialized tooling, technical drawings, and manufacturing processes that had made jet production possible. Allied engineers studied these facilities with the reverence of archaeologists examining artifacts from a more advanced civilization, recognizing that they were witnessing technologies that exceeded anything their own industries had achieved. The aircraft themselves proved only part of the treasure that Allied forces uncovered. In hidden archives and protected vaults, investigators found thousands of technical documents that detailed every aspect of jet engine design, manufacturing, and operation. These papers contained the accumulated knowledge of years of experimentation and refinement metallurgical formulas for high-temperature alloys, precision manufacturing techniques for turbine blade production, and aerodynamic data from wind tunnel tests that had pushed the boundaries of high-speed flight. Perhaps most valuable of all were the German engineers and scientists who had created these revolutionary machines. Men like Hans von Ohain, who had pioneered jet propulsion itself, and Willy Messerschmitt, whose swept-wing designs had solved problems that Allied engineers didn't even know existed, found themselves courted by former enemies eager to understand the principles behind German technological superiority. These intellectual resources proved more valuable than any material capture, as human knowledge could be transferred instantly while manufacturing capability required years to develop. The interrogation centers where Allied forces processed, captured German aviation personnel became informal universities where the secrets of jet flight passed from defeated enemies to victorious allies. Hans von Ohain, working with American investigators, explained the thermodynamic principles that made jet propulsion possible while demonstrating calculation methods that revealed the mathematical relationships governing high-speed flight. His knowledge would directly influence American jet engine development programs that produced the power plants for Cold War aviation supremacy. Willy Messerschmitt's swept-wing innovations created particularly intense Allied interest, as his accidental discovery of high-speed wing design had solved aerodynamic problems that would become critical as aircraft approached the speed of sound. The 18-degree sweep angle that Messerschmitt had adopted for practical ground clearance reasons proved nearly optimal for delaying the onset of compressibility effects that limited conventional straight-wing aircraft. This knowledge would revolutionize post-war fighter design and make supersonic flight practical for operational aircraft. The transfer of German jet technology to Allied nations occurred through multiple channels that reflected the complex political relationships emerging from victory over the Nazi regime. American Operation Paperclip brought hundreds of German aviation specialists to the United States, where they joined programs at Wright-Patterson Air Force Base, Bell Aircraft, and other facilities developing America's next generation of military aircraft. These German engineers found themselves working alongside former enemies to create aircraft that would defend against their former homeland's new Soviet occupiers. Soviet forces, advancing from the east, captured different but equally valuable portions of German jet technology. The Junkers engine manufacturing facilities in central Germany fell into Soviet hands, along with technical personnel who had developed the Jumo 004 power plants that made Me-262 operations possible. This captured knowledge would accelerate Soviet jet development programs and contribute to aircraft like the MiG-15 that dominated early Cold War aerial combat. British investigators focused particularly on capturing examples of operational German jets, understanding that flight testing intact aircraft would reveal performance characteristics and handling qualities that technical documents could not convey. Several Me-262s fell into British hands in flyable condition, providing Royal Air Force test pilots with opportunities to experience firsthand the revolutionary flight characteristics that had given German pilots such overwhelming advantages during the war's final months. The influence of German jet technology on post-war aviation development proved immediate and profound. North American aviation's F-86 Sabre, which would dominate aerial combat during the Korean War, incorporated swept wings derived directly from Messerschmitt's research, along with engine air intake designs that reflected German solutions to high-speed airflow management. The aircraft that established American air superiority in the 1950s owed its most critical design features to technology captured from defeated enemies. Soviet aviation development followed parallel paths that reflected their capture of complementary German technologies. The Mikoyan Gurevich MiG-15 that challenged American air superiority over Korea incorporated swept-wing designs inspired by German research, while its power plant derived from British jet engine technology that Stalin had acquired through diplomatic channels. This convergence of captured German aerodynamics with British propulsion technology created aircraft that matched American performance despite Soviet industry's relative technological backwardness. The psychological impact of German jet technology extended beyond immediate military applications to transform civilian understanding of flight's possibilities. Allied pilots who flew captured Me-262s discovered that aviation had crossed a threshold into a realm of speed and performance that made pre-war aircraft seem obsolete overnight. The sensation of jet-powered flight smooth, vibration-free acceleration to velocities that compressed time and distance revealed that humanity had entered an age when crossing continents would require hours rather than days. Commercial aviation applications of jet technology emerged naturally from military developments, as aircraft manufacturers recognized that civilian passengers would demand the speed and comfort that jet propulsion could provide. The same principles that had made Me-262s nearly invincible in combat high-speed efficiency, high-altitude capability, and smooth operation would revolutionize air transportation by making intercontinental travel accessible to ordinary citizens rather than just wealthy adventurers. The manufacturing techniques that German industry had developed for producing precision jet engine components influenced post-war industrial development far beyond aviation applications. The quality control procedures, metallurgical processes, and precision machining capabilities required for turbine blade production found applications in power generation, industrial manufacturing, and countless other fields where high-performance machinery demanded unprecedented reliability and precision. Test data captured from German wind tunnel facilities accelerated Allied understanding of high-speed aerodynamics by providing experimental results that would have required years of independent research to duplicate. These measurements revealed the behavior of airflow over swept wings at velocities approaching the speed of sound, while pressure distribution studies showed how conventional aerodynamic theory broke down as aircraft entered the transonic regime where jet fighters operated. The training manuals and operational procedures that German forces had developed for jet aircraft provided Allied air forces with starting points for their own jet pilot training programs. The techniques that German pilots had learned for managing temperamental early jet engines, the emergency procedures developed for high-speed flight, and the tactical innovations that made jet combat effective, all transferred to Allied forces who found themselves inheriting not just aircraft technology, but the accumulated experience of operational jet warfare. Engine test data proved particularly valuable as Allied manufacturers discovered the metallurgical challenges and operational limitations that German engineers had identified through painful experience. Turbine blade failure modes, fuel system requirements, and maintenance procedures that had been developed through trial and error during wartime operations provided Allied engineers with knowledge that prevented them from repeating German mistakes while building upon German successes. The influence of captured German jet technology extended into the space age itself, as rocket propulsion principles that had powered German V-2 ballistic missiles combined with jet engine technologies to create the foundation for humanity's expansion beyond Earth's atmosphere. Engineers like Wernher von Braun, who had developed rocket technology in parallel with jet engine research, found themselves applying their knowledge to American space exploration programs that would eventually carry humans to the moon. Material science advances that German engineers had achieved in developing high-temperature alloys for jet engine applications influenced post-war industrial development across multiple sectors. The understanding of how metals behaved under extreme temperature and stress conditions found applications in power plant construction, chemical processing, and manufacturing processes that required materials capable of withstanding conditions that conventional alloys could not survive. Tomorrow, we will explore how this extraordinary convergence of captured German technology, Allied engineering expertise, and Cold War competition transformed aviation from an experimental curiosity into the foundation of modern transportation, communication, and exploration that connects every corner of our planet and reaches toward the stars themselves. Standing at the edge of a modern airport runway, watching a commercial airliner accelerate into the sky with 200 passengers aboard, we witness the culmination of a journey that began in Hans von Ohein's secret workshop 8 decades ago. The thunder of jet engines that now carries humanity across continents in hours traces its lineage directly to that first experimental flight of the Heinkel. He-178, a 6-minute demonstration that opened the door to an age of speed that has fundamentally transformed human civilization itself. The principles that German engineers discovered in their desperate quest for aerial superiority during World War II now govern every aspect of modern aviation, from the smallest business jet to the largest passenger airliner. The swept wings that Willy Messerschmitt adopted for ground clearance reasons have become universal features on aircraft that routinely operate at velocities that would have destroyed conventional straight-wing designs. The turbojet engines that promised to save the Third Reich instead liberated humanity from the constraints of distance and time. Consider the extraordinary transformation that jet propulsion has brought to human experience. A journey from New York to London that required 5 days by ocean liner in 1939 now takes less than 7 hours by commercial jet, while routes that connect opposite sides of the Earth can be completed in a single day. The mathematical relationship between distance and time that governed human movement for millennia has been fundamentally altered by technology that began as a weapon of war but evolved into an instrument of global connection. The commercial aviation industry that emerged from military jet development represents one of the most remarkable examples of technological transformation in human history. Airlines that began operating jet aircraft in the 1950s discovered that passengers would pay premium prices for the speed, comfort, and reliability that jet propulsion provided. The smooth, vibration-free flight characteristics that had made military jets effective weapons proved equally valuable for civilian transportation, while the high-altitude capability of jet engines allowed aircraft to fly above weather systems that plagued propeller-driven aircraft. The Boeing 707, which entered commercial service in 1958, demonstrated how military jet technology could revolutionize civilian transportation. This aircraft incorporated swept wings derived from German research, turbojet engines based on principles that Hans von Ohain had pioneered, and high-altitude flight capabilities that made transcontinental travel comfortable and reliable. Passengers who had endured long, uncomfortable flights in propeller-driven airliners discovered that jet travel offered an entirely new experience that compressed both time and distance. The psychological impact of jet-powered flight extended far beyond transportation convenience to transform human perception of the planet itself. Passengers who could fly from sunrise to sunset while crossing multiple time zones experienced the Earth's rotation in ways that previous generations could never imagine. The curvature of the horizon became visible from jet aircraft cruising altitudes, while the speed of flight compressed diverse landscapes and cultures into journeys measured in hours rather than weeks. Modern jet engines represent evolutionary descendants of the primitive Junkers Jumo 004 power plants that struggled to operate for 12 hours without failure. Contemporary turbofan engines routinely function for thousands of hours between major overhauls, while their fuel efficiency and reliability have made air travel accessible to billions of people worldwide. The metallurgical challenges that defeated German engineers have been solved through advanced alloys and manufacturing techniques that create turbine blades capable of operating under conditions that would instantly destroy 1940s technology. The fundamental physics that govern jet propulsion remain unchanged since Hans von Ohain first demonstrated controlled gas turbine operation in Ernst Heinkel's workshop. Air enters the front of the engine, mixes with fuel in combustion chambers, burns continuously, rather than in discrete explosions, and exhausts through precisely shaped nozzles that accelerate hot gases to tremendous velocities. Newton's third law of motion still provides the action and reaction that pushes aircraft through the sky, but engineering refinements have transformed crude experimental devices into precision power plants that operate with mechanical perfection that early pioneers could never have imagined. The swept-wing aerodynamics that Messerschmitt discovered accidentally have been refined through decades of research that revealed the mathematical relationships governing high-speed flight. Wind tunnel testing and computer modeling have optimized wing designs for specific flight regimes, while understanding of transonic and supersonic aerodynamics has enabled aircraft to operate safely at velocities that approach and exceed the speed of sound. The Concorde supersonic airliner, which carried passengers at twice the speed of sound for 27 years, represented the ultimate expression of aerodynamic principles that began with German wartime research. Military aviation has evolved far beyond the primitive jets that first appeared over European battlefields in 1944. Modern fighter aircraft routinely exceed twice the speed of sound, while incorporating stealth technologies, advanced radar systems, and precision weapons that would seem magical to pilots who flew Me-262s. Yet these sophisticated machines still depend on the fundamental design principles that German engineers established: swept wings for high-speed stability, turbojet propulsion for sustained high performance, and tricycle landing gear for safe ground operations. The space age itself emerged from the convergence of jet propulsion technology with rocket engineering that German scientists had developed in parallel programs during World War II. The same metallurgical advances that made jet engines possible also enabled rocket engines capable of achieving the velocities necessary for orbital flight, while the manufacturing precision required for turbine blade production provided the quality standards essential for space exploration. Human expansion beyond Earth's atmosphere became possible through technologies that were refined in the crucible of wartime. Necessity. Environmental consciousness has driven recent developments in jet engine technology toward greater fuel efficiency and reduced emissions, creating power plants that produce more thrust while consuming less fuel and generating fewer pollutants. These advances reflect the same innovative spirit that characterized German wartime research, as engineers continue pushing beyond the boundaries of existing technology to solve problems that previous generations considered impossible. The global economy that connects every corner of the modern world depends fundamentally on jet-powered transportation for both passengers and cargo. International business, scientific collaboration, and cultural exchange occur at scales that would be impossible without aircraft capable of crossing oceans in hours rather than weeks. The speed of modern communication may be measured in milliseconds, but the movement of people and goods still requires the physical transportation that only jet aircraft can provide efficiently over intercontinental distances. Maintenance procedures and operational techniques that modern airlines use for fleet management trace their origins to the lessons that German engineers learned while struggling to keep temperamental early jets operational under wartime conditions. Quality control procedures, preventive maintenance schedules, and parts inventory systems all reflect knowledge gained through the painful experience of operating revolutionary technology under extreme circumstances. The training programs that prepare modern airline pilots incorporate techniques that German test pilots developed while learning to handle aircraft that moved faster than human reflexes could follow. Crew resource management, emergency procedures, and the systematic approaches to high-speed flight all build upon foundations that were established when aviation first crossed the threshold into the jet age. At air shows around the world, reproduction Messerschmitt Me 26 2s still demonstrate the revolutionary flight characteristics that amazed observers 8 decades ago. These faithful recreations, powered by modern jet engines that provide the reliability that original Junkers power plants could never achieve, serve as flying museums that preserve the memory of humanity's first steps into high-speed flight. Watching these aircraft perform reveals how far aviation technology has advanced while honoring the courage of engineers and pilots who opened pathways to the future under the most desperate circumstances imaginable. The story that began with Hans von Ohein's quest to harness the power of controlled explosion continues today in research laboratories, where engineers develop hypersonic aircraft capable of crossing continents in minutes rather than hours. These next-generation vehicles will operate at velocities that make current jets seem slow, while their propulsion systems will combine the principles of jet and rocket technology to achieve performance that pushes toward the boundaries of atmospheric flight itself. As we stand on the threshold of routine space travel and hypersonic transportation, the legacy of German jet pioneer research continues to influence every aspect of high-speed flight. The courage to challenge conventional thinking, the persistence to solve seemingly impossible engineering problems, and the vision to see beyond immediate limitations. These qualities that characterized wartime German aviation research remain essential for pushing humanity toward new frontiers of exploration and discovery. The age of fire that began with contained explosions in secret workshops has evolved into an era where jet engines carry us not just across the Earth, but toward the stars themselves. Tomorrow's aircraft will travel faster and farther than today's machines, but they will still depend on the fundamental principles that visionary engineers discovered when they first learned to harness the fury of burning gases. For the ancient human dream of swift, effortless flight through the infinite blue sky that connects all horizons. In the end, the story of Nazi Germany's jet fighters reveals a profound truth about human innovation, that knowledge transcends the circumstances of its creation, flowing like water through the barriers that divide nations and ideologies. The technology that was born from desperation and nurtured by conflict ultimately became the foundation for peaceful progress that has connected our species across the vast distances that once separated us. This is the true legacy, written in aluminum and fire, not weapons of destruction, but wings of liberation that carry humanity toward futures limited only by the boundaries of imagination itself.